So welcome everyone. Before I introduce the speaker, let me repeat the tedious part. You are on mute. You won't be able to ask directly any question to the speaker. But in case you want to ask a question, please type it in the Q&A box. Please don't use the chat box, but the Q&A box. I will check this box regularly. From time to time, I will interrupt the speaker and ask your question on your behalf. Okay, I hope that's clear for everyone. But feel free to ask any question you have in this way. Perhaps I will leave some question for the end of the talk. And that's it for the organization. So let me introduce the speaker, Stephan Mandt, who is now assistant professor of University of California, Irvine. Before that, Stephan was working at Disney Research in Pittsburgh, if I'm not mistaken. Mm-hmm. So the connection between Disney and movies and important sampling and Monte Carlo is not so surprising if you follow the news. There was been, I think, 1 or 2 Oscar awards that were given to people working on Monte Carlo for special effects. I'm sure Stephan knows more about this, perhaps even from Disney Research. So Stephan works on different things related to Bayesian methods for machine learning and Bayesian deep learning, variational based, as you can see from the title. So without further ado, please let's welcome Stephan, who's going to talk about compressing variational base. Thank you, Stephan.
All right. Yeah, thank you, Nicholas. Yeah, it's a great pleasure to be here in this exciting seminar series. As Nicola already announced, the title of my talk is Compressing Variational Base, and as the title already suggests, so this is really adopting essentially, the variational autoencoder paper, but really pointing it into a new direction on where can we actually drive these methods of Bayesian deep learning and how they are actually useful for our goal of data compression. So let me actually start by saying something pretty obvious. Namely, we already experience a lot of deep learning all around us. It already affects all areas of our lives. And actually most of deep learning that's deployed in industry is actually deterministic deep learning. However, we also realized in particular in the last couple of months that deep learning has become increasingly expensive. So this figure here that you see here is taken from an NVIDIA blog, and it shows you essentially the growth that different deep learning architectures have experienced over the last couple of years, ranging from relatively simple architectures for image classification with a couple of million parameters, up to the first generation of these kind of big language models, and then nowadays reaching billions of parameters. So actually this plot is not even up to date. So everybody, I guess, has heard already about GPT-3, which has over 100 billion parameters, and actually took the equivalent of several cars' lifetime CO2 emissions to be trained. So all of this is incredibly resource inefficient and expensive. And the question then is, how can we actually design a new generation of deep learning that is more resource efficient? And in particular, we want to focus here on different aspects of efficiency, namely efficient in terms of computation, efficiency in terms of the use of training data, and also efficiency in terms of storage, right? And all of these 3 different aspects are going to be covered in today's talk. Here's one more slide on this. So how can we make Bayesian, or how can we make deep learning more resource efficient? And again, the claim here is that, of course, the solution is going to be Bayesian, right? So Bayesian deep learning already provides the answer to a more resource efficient generation of deep learning. And the couple of questions that we want to answer is, how can neural networks model more information from sparse data? The solution here is to actually choose informative prior. So think of time series models, and we'll see a couple of examples here. How can we make them more storage efficient? So in other words, how can deep learning be used to compress models or parameters? And this is actually going to be what I'm mainly talking about today. So the solution here is, using variational inference for data compression, and that's a pretty new and exciting field. And I'm going to talk about that for the majority of today. And then finally, we also want to cover a little bit of runtime efficiency. So which types of training paradigms are actually the fastest or the best suited for resource efficient learning, right? And this is again something that might be obvious for some of you, but variational inference is oftentimes allowing you a really good trade-off between exactness and speed, right? And I'm going to present here an interesting algorithm that hybridizes MCMC and variational inference in a certain way. Okay. So let's talk a little bit about the first step. And again, I don't want to spend too much time on this, but how can we make representation learning more data efficient? Right? And to this end, I want to look at a particular example where we are interested in learning vector representations of words, but we want to do this on historical data, for example, historical books. And in doing so, we're interested in how does language evolve over many centuries and how words change their meaning over time. So the first naive thing you can do is you kind of split your corpus, for example, your Google Book corpus, into many individual years. And then you're trying to train word2vec or some other word embedding model on these individual years. And you want to use that in order to see how language evolves. Now, the problem is that depending on which training corpus you use, you might have actually huge vocabularies, and you might not even observe every word in every moment in time. So you're really suffering from data sparsity, even though and as a whole, you might have a lot of data available because you're looking at hundreds of years of digital books. So how can we solve this task of learning sort of a dynamic word embedding model on data that actually experiences a distribution shift so that we cannot easily learn separate word embeddings in individual years? And the Bayesian solution to that is to kind of just combine a probabilistic version of word2vec with a latent Kalman filter as a prior. So in other words, we're kind of tying these word embeddings together over time. We're assuming that they're only moving very smoothly and slowly. And now we're training the whole model end to end. So this leads to the so-called dynamic word embeddings model that I came up with my postdoc Robert Bambler a couple of years ago. So this is the movie that comes out of it. If you train the model and you play the movie, visualizing how the word cloud evolves over time. So what you see here actually is, again, the semantic space of word2vec evolving over many years. We're focusing on the 1930s, and we're also focusing on one particular word, namely the word broadcast, which experienced a strong semantic shift in these years, ranging from its original meaning in agriculture over to its modern meaning in broadcasting media technologies. And you can clearly see that this word evolves over time in a pretty smooth fashion. So what the model also allows you to do is, hold on. What the model allows you to do is to ask or query your fit, about what are actually the 10 fastest moving words in the last 150 years in terms of differences between the embeddings in the year 1850 and 2008. And this is the list that pops out, right? So those are the fastest moving words. Let's actually zoom in and look at one particular example. So here's the word peer. What you see here is that, as a function of time on the x-axis, you look at the similarity of certain other words, the context words, to that word peer. And we highlighted here the 5 words that were the most similar in 1850. Those are the red words, and they kind of become more dissimilar over time, and contrasted them to the most similar words at present, and those are the blue words. And you see that the word peer essentially moved away from something like a nobleman, think of the House of Peers in Britain, to somebody who's more of equal standing, like your parents or a teacher. And so this is almost quite the opposite, and the model picks it up automatically. So why couldn't we do this just naively by training an individual word embedding model on on 2 subsequent years and just compare the word embeddings one by one? So this is a plot of the word embeddings in 1 year. And if you would then kind of separately train a word embedding model in the next year and kind of draw errors between these individual word embeddings, you'll just see a big mess, right? So essentially all words move according to this assumption. And this is, of course, a very unreasonable assumption, right? So the signal of individual words changing their semantic meaning totally gets lost in the noise. So in contrast, if you look at the dynamic word embedding model that kind of really only allows for significant changes, you get a much sparser answer, and you kind of really only see the individual words that change, right? And so this is a good example why Bayesian can help, right? Under distribution shifts, you can basically construct an informative prior. So in this example, it's a time series prior, combine it in a pretty much arbitrary way with a whatever deep learning architecture or word embedding model, and train everything jointly, and thereby solving some aspects of data efficiency. Okay. So next, I also want to talk about other forms of data efficiency, and in particular embedded in deep architectures. But nowadays, I'm not looking at word-to-back, but I'm rather looking at a more general architecture, which is the variational autoencoder. I'm sure most of you are pretty familiar with this model, but let me nevertheless spend 1 or 2 minutes on this. So what is a variational autoencoder? It's essentially a deep generative model that you see on the left-hand side. You know, you start with some low-dimensional vector representation, which you can think of as random noise, and you push it through a neural network with parameters theta to generate an image or some high-dimensional data point x. Right? So now you can wonder, how do you train this? You have to basically simultaneously infer the latent variable z, and you also have to train the model parameters theta. And one of the fastest and most efficient ways to do so is to actually train what's called an inference network, or an encoder that's essentially a mapping from the image to the noise distribution that predicts an approximate posterior over z and has parameters phi. And now you plug both of them into the KL divergence and jointly optimize with respect to theta and phi. Right? So this is essentially the probabilistic autoencoder that we want to work with. So one model that essentially historically was important for me because it kind of really raised my interest in data compression is this so-called disentangled sequential autoencoder, or sequential variational autoencoder, it should be actually, that we came up with. So the idea is that back then when Yingzheng Yang worked with me at Disney Research for a couple of months over the summer, we really wanted to, first of all, work on a generative model for video, which back then was pretty novel. But also we wanted to analyze whether we can actually find so-called disentangled representations in video. So what do I mean by that? So what I mean by that is, can we separate out factors of variation that are essentially responsible for the dynamics from factors that are encoding the shape of these objects that are depicted in the image, right? And once we learned such a model, we can then conditionally generate videos. So for example, what you see here on the top, on the bottom left video, you see all sorts of randomly generated sprites videos that are very similar to our training data. Then in the middle, you see a lot of videos that actually share the appearance. And on the right-hand side, you see videos that share the dynamics but have different appearances. So this is something we achieved. And the way we achieved it is shown on the graphical model on the top right here, where we have a graphical model that has that conditions on a data sequence x1 through xt. And it has 2 sets of latent variables, namely a global variable f that is affecting every single frame of the video, and that encodes static attributes. And we have an underlying latent time series z1 through zt, which is supposed to encode dynamics, right? And so the claim here was, by just designing this graphical model and properly training it, we can automatically discover these disentangled representations. So here are a couple of interesting things you could do with this model. So for example, you can use it to manipulate data in an interesting fashion. So when you look at your training data, you could encode it. You know, this converts your sequence of f's to a state f, sorry, your x sequence into f and a sequence of z's. And now you can swap one of these 2 different sets of latent variables, right? So in one case, you could kind of essentially swap z, and then you kind of get and then you decode and you get a new data sequence that share the appearances but display different dynamics. And in the other extreme, when you encode it and you're swapping, you're keeping z but you're swapping f, then you generate videos that essentially share the dynamics but have different appearances. Okay, so this is a pretty curious model. But the real reason it became important for my research is that we wanted to answer the next question, namely, can these generative models for video actually really use for video compression, right? It's somewhat clear that if you're good at predicting the next frame in a sequence of frames with high accuracy, that this should be somehow useful for video compression. But how exactly, right? How exactly do you have to convert a deep generative model such that it becomes a useful compression architecture? And to this end, we looked a little into the literature and found a bunch of papers on image compression. And in particular, Johannes Ballet is one of the main leaders here in this field who published on using pretty much a variational autoencoder architecture for getting state-of-the-art image compression performance. And this is the computational diagram that you see is shown here on the top plot. So it's basically a variational autoencoder where you encode an image, you get a mean encoding mu, and then depending on whether you train the model or you use it for compression, you either inject noise. So this is during training, right, where you train a variational autoencoder, you're kind of injecting noise to the latent state. But let's assume we're talking about compression. So then actually you would round this latent state mu, right? And the fact that during training you injected this sort of noise guarantees that the model is actually robust to this rounding operation, right? When you round your latent state to the nearest integer, you're not really destroying valuable information. So now you have a discretized latent state z twiddle, and you use the prior that you've learned to entropy code this discretized latent state. So now you get a binary representation. And then when you decode it, you kind of just use, again, the prior to convert the binary bit string into a discretized vector z twiddle, which you then decode, right? So this is an end-to-end image compression architecture. And it's really important that you're combining, that you're using these VAEs not only for dimensionality reduction, but that you're really using the prior to also entropy code your discretized latent states. So after having learned about these tricks, we actually came up with one of the first video codecs that we published at NeurIPS 2019. And it's essentially a generalization of the Ballet idea to our disentangled variational autoencoder model, right? So what you see here is pretty much a copy of that architecture. But now we have the frame sequence x1 through xt that gets encoded into the global state f, which we then discretize and entropy code with a prior, which is static. That is p theta of f twiddle. And at the same time, we're also encoding these individual frames xt using a sequential prior. That is essentially the sequential prior of our sequential variational autoencoder, right? And both get entropy coded, and again, by decoding, we're combining them again, and this allows us to compress videos. So this is kind of our first attempt here, and I should say we got promising results on low resolution video, in particular if we trained and tested on very similar content. So what you see in the top plot here are so-called rate distortion curves, where we kind of measure essentially how does the quality degrade as we reduce, as we compress more and more aggressively. In other words, as we kind of decrease the bit rate. And a good algorithm should be somewhere in the top left corner, right? And we see that the neural architectures that are all shown, which are versions of our model, are better than the classical architectures. However, I also want to say here that this is really a first attempt in the sense that we only looked at low resolution videos, and actually looking and getting competitive performance on high resolution is much, much more difficult. And this is kind of where many intelligent people try to get good answers. And we are actually also working on this, scaling it up to full resolution at the moment. Okay, so now we are kind of, starting from the first topic of data efficient learning, which we analyzed in terms of time series models. We've migrated to the next topic, which is about storage efficient learning, right? So how can we use variational autoencoders in deep generative models to also learn efficient representation of model parameters and also efficient representations of data? And again, the claim here is that variational inference is the answer. So let me kind of cover the broad background of variational inference before we get into the technical details first. And in particular, since this is a talk series about Bayesian deep learning or scalable Bayesian modeling, let me actually be pretty brief here, because I assume that a lot of you have already a decent background on this topic. So what do we want to talk about?
Stephan?
Yes.
Sorry to interrupt, but we have a question.
Oh yeah, of course.
So Tan Dungle, sorry if I mispronounce your name, says, with a limited amount of clinical notes, real data from the doctor's narrative at the hospital, it is shown that generative learning approaches such as variational inference, VAEs, transformers, even through BERT, etc., cannot effectively compete with the conventional TF-IDF for representation learning of the clinical notes. Do you have any comments on that issue when we can only apply these advanced techniques with a large amount of data? Thank you for your answer.
Yeah, that's a good point. So yeah, I think yeah, representation learning for data is for text data is a whole different thing than representation learning for dense data such as like images or video. So clearly, most progress on deep generative modeling has been on the dense data side, right, where neural networks are really kind of easily capable of learning hierarchical feature representations. So I think for text, it's a whole different level and a whole different question. And yeah, I mean, it's true that also variational autoencoders don't work very well on text. And yeah.
Okay, thank you. You can proceed if you want.
All right. All right, thank you for the question. So then let's talk about, again, very briefly, variational inference. We have a probabilistic model over latent variable z and data x. That factorizes into a likelihood and a prior. We're interested in the posterior, p of z given x. And the idea is to, instead of computing the posterior exactly, we're kind of approximating it with a simpler distribution, q of z, that has certain parameters lambda. So this is the picture that you should have in mind. We have a potentially bimodal posterior distribution that we cannot compute. And we use a simple family of distributions q that have tuning parameters lambda that we match as good as we can to that posterior distribution. And matching really means minimizing Kalbeck-Leibler divergence between these two different distributions. So this is the objective function that variational inference maximizes. So it's also called the evidence lower bound because it's a lower bound to the marginal likelihood p of x of the data. So here I'm writing it in a slightly more general form, and I'm decomposing the evidence lower bound that is now really a function of the variation parameters lambda into what I call a distortion, namely the expectation under q of the log likelihood, minus beta times the KL divergence between the variational distribution q and the prior p. Right? And in order to really get that variational bound, you have to set usually beta to 1. Sorry, there's a question?
Yes, sorry to interrupt again. We have a question from Justin. Didn't see it before, so maybe it was about something a few slides ago. Is this applicable to lossless compression, or will this be intractable because of the difficulty of density estimation in the original space?
It's a good question. So I think actually you can also do lossless compression. So I mean, there's actually an active literature also on using what's called bit-spec coding to kind of get really good competitive performance for lossless compression. So yeah, I think there's no reason not to try lossless compression also. I mean, all you need is a good density estimator in your discretized space. And yeah.
Thank you.
Actually, not a lot of people look at video compression in the lossless case, but I think it should be possible. I mean, it might be just too high dimensional, but there's no fundamental reason not to do it. Okay, thank you for the question. All right, so this is the elbow, evidence lower bound. As I said, usually you pick beta equals to 1, but what actually happens if you set beta to 0? So in other words, when you only care about distortion, when you then allow a flexible class of distributions Q, you can easily convince yourself that the optimal solution to only optimizing for distortion is to essentially pick a delta distribution and place it under the maximum likelihood mode of the posterior, right? So in other words, the distortion term really only cares about explaining the data as well as possible. And it doesn't really care about any uncertainty estimates or any matching to the prior. And then in the presence of this rate term, in other words, when beta equals to 1, the model really tries to find a compromise between fitting the data and matching the prior. And you kind of get this nice matching between the variational distribution and your posterior. Right, so this is kind of the picture that you should have in mind. So how is this beta variational autoencoder then relevant for data compression? So essentially, you can do data compression with a simple variational autoencoder as follows. So first of all, you train your beta VAE at a certain value of beta that corresponds to a certain rate distortion trade-off. And the first step then is to, when you use this for compression, you take a data point X and you're mapping it to Z space using typically, the maximum mode of your Q distribution, right? So you most likely Z would be then taken as a representation of your data point X. The second step here, which is also shown on the right-hand side, is this rounding step or quantization step. And that's really important because if you want to do entropy coding, you have to work with discrete states, right? You can store arbitrary many bits in a real valued number. So you have to kind of chop up the digits at a certain point. So you round. So that's step 2. And the third step is then to entropy code Z star using your prior. And this ultimately gives you your compressed bit string. So you can actually do this both for data compression and for model compression. So left-hand side, you see a VAE. On the right-hand side, this kind of shows you that you can do this also for models such as, for example, probabilistic word embeddings. And we'll actually see examples of that in the next couple of slides. So having said that, I want to kind of address a particular weakness of the current approach, right? So if you look closely at the VAE for compression literature, most people actually don't really exploit the posterior variances. In fact, they're setting the posterior variances to a fixed value that guarantees that you can round at that particular standard deviation of that posterior variance. But a real variational autoencoder is actually much more powerful, right? I mean, you learn for every data point, you get an individual variance estimate of your posterior. So how can we actually exploit that, right? So how can we make better use of the posterior uncertainty in data compression? So this is the first project that I would like to discuss in this context. And before we do that, I want to kind of point out that we as humans, we sort of automatically do that, right? When we talk about data, we automatically round the numbers that we talk about in a meaningful way. So just to kind of give you an example, if you kind of ask me what's the population of Rome, you know, I might want to, you know, if you're referring to the present, I might look it up on Wikipedia and kind of give you a very exact number as an answer. But if you ask me, you know, no, I actually meant the year 500 AD, and then I would look up again, maybe in my textbook, and would say, well, approximately 100,000, right? And of course, the reason why I would give you a different answer here is that there's much more uncertainty associated with the year 500, right? And so I'm kind of automatically incorporating the uncertainty into the estimate that I would give. So can compression algorithms do the same? In other words, you know, can we kind of automatically include uncertainty estimates to get better rate distortion performance? To kind of contrast this a little bit to the conventional way of dealing with compression is that probability estimates are already very well taken care of in this world, right? So the conventional wisdom of data compression is to say that you don't transmit what you can predict. You know, we already did that for video compression, and a simple you know, consequence of that is that better generative models lead to better data compression, right? And we've already seen that because you can better estimate the entropy of the data distribution, or you can better approximate the data distribution. The better you can approximate the data distribution, the better you can compress. So this is very well known. And kind of to give you an example of how this is done, I want to talk about very briefly about lossless compression, because it's going to be important to understand our idea. So this is so-called arithmetic coding. And that's a way of actually really using or exploiting uncertainties in your compression scheme. So let's assume you want to encode the outcome of a draw of a 10-sided dice. And let's assume that it has a certain non-uniform distribution, illustrated by these histograms. The first thing that we do in arithmetic coding is actually we look at this discrete distribution, and we're looking at its cumulative distribution. And it turns out there's an upper cumulative and a lower cumulative, depending on not whether you kind of count the outcome of that particular draw that you currently are, you know, to that cumulative. So you kind of, in other words, you're summing up all of the events up to that event, or including the event, right? And so this gives you an upper and a lower cumulative distribution. And what you do then is, if you observe a certain outcome, like a 7, you're kind of looking it up, and you're mapping it onto the interval 0 and 1. Essentially, you're mapping it to a subinterval that corresponds to the dashed vertical line of the difference between the upper and lower cumulative distribution that you're working with, right? So this gives you a particular position now on this interval. And among all of the different you know, numbers that you can use as a representative of that interval, you pick the number that has the fewest number of decimal places, right? And in this example, it's 7/8, which has exactly 3 decimal places in binary representation. If you would round more aggressively, you would kind of use, you know, 3/4, but this would be out of your uncertainty region, right? So you have to use 0.111, which is the shortest representation of the outcome 7 in this particular example, right? So this is what's called arithmetic coding. Of course, you can reconstruct that message based on that binary representation 0.111 by just kind of doing the process in reverse. So this is an example of lossless compression. So what we do, what we want to do instead is compressing according to a different principle, namely to not transmit what we are not sure about, right? So this is very different from the paradigm of not transmitting what we can predict. So we really want to, you know, take uncertainty estimates into account. So how could we possibly do that? Let me give you a particular example where we really use posterior uncertainties for compression. So let's assume you want to do model compression, and we're looking at a very simple example of linear regression where we're in one dimension. We have data points which are x and y pairs. You know, we just want to, and we really want to encode now the model that best fits the data. In other words, we want to encode the simple one-dimensional line. How do we want to do that? Well, first, you know, if we look in parameter space, this green line here corresponds to a point of a particular value for the slope A and the offset B, right? But in general, this point will have arbitrarily many decimal places. And so now we want to compress it and round it. So one naive way to do that would be to kind of just choose some uniform grid and just take the nearest grid point as a representation for that parameter vector AB. Right? So this would give you that point. And then if you map it back to that you know, original data space, you know, you would get a distorted version of your compressed model, right? So this could be the dashed line that you see here, right? Okay. So this is clearly not very good. How can we do it better? We can do it better by being Bayesian, and to actually know that we can formulate linear regression also as a Bayesian model, right? Bayesian linear regression. And so in other words, we really don't only know the most likely point AB in parameter space, but we know an entire distribution. We get an ellipsis that kind of characterizes an uncertainty region of parameters. And we know it's actually much more important to efficiently encode A than to efficiently encode B, because there's much less uncertainty associated with, there's much more certainty associated in A with than compared to B. So what we can do then is we pick a variety of grids, and you know, in such a way that different grids are more or less expensive. So for example, you could imagine that they are they correspond to you know, every grid has a fixed number of decimal places, and grid points that have more decimal places are more expensive to encode, because then you have to kind of work with higher precisions. And so what we would do then is we'd probably just pick a point that is still on this grid, but which ultimately has high posterior likelihood, right? In other words, we're kind of really breaking the symmetry between A and B, and we're really investing more bits in encoding A than we would invest in encoding B. And if we do that, and we use this other grid point for pretty much the same number of bits and reconstruct it, we get a much more accurate reconstruction of the original model, right? And so this is essentially the idea that we really want to incorporate uncertainty into compressing our models. Okay. So here's another technical slide on how we do that. And to understand the approach, it's really important that you kind of remembered how arithmetic coding worked. So what we proposed here in this recent ICML paper is a new way of compressing data in a trained variational autoencoder, which is in some sense optimal. Right, and what I mean by that is that we're kind of really we're really making use of the full posterior uncertainty that you've already learned and which is already evident in your variational distribution cube that predicts different variances for different data points. So how do we do that? So first, let's do the naive thing and try to translate arithmetic coding to the continuous domain, right? Because we ultimately work with continuous data such as images. Right, so we pick a prior distribution over events, which could be a simple Gaussian distribution, and we're computing its cumulative distribution. Right now, there's no upper and lower cumulative, there's only one cumulative. and use that to encode or to map individual outcomes of the real valued number to the interval 0 and 1. So in other words, if we make an observation and we observe a certain value, we look it up and we map it to the interval 0 and 1. Now the problem is that this doesn't give us any compression, right? Because if we do that for an arbitrary point, essentially with probability 1, following this recipe, you will end up with a real valued number that has infinitely many decimal places. However, if you think of approximate Bayesian inference, what we really have is not only the most likely encoding of an image, say, but we rather have an entire approximate posterior, which is Gaussian, right? And so what we do now, roughly speaking, is to not only look at the most likely encoding mu I, but we also look at the corresponding uncertainty region, plus minus sigma I, and we're mapping the whole thing to the y-axis, in other words, the interval 0 and 1, and we're getting an entire curve out of it. And there is a certain region or a certain subregion which corresponds to valid encodings of that particular data point, right? So any representative that we would choose on the interval 0 and 1 in the red interval would be a valid or a decent encoding of our variational distribution. But now actually the answer is no longer unique, so you can do different things. There's a trade-off at play. So for example, you could pick 0.111 as your encoding for that outcome. And the nice thing about that is that you're kind of in a higher density region of your approximate posterior. So when you kind of decode that value, you would get an answer that is closer to mu I, which is in some sense the optimal result. But you could also decide to pick 0.11 modulo in binary string. If you do that, you're still in the uncertainty region, but you get a poorer reconstruction out. On the other hand, you're only wasting 2 bits as opposed to 3 bits, right? So in other words, there is a rate distortion trade-off at play, even in the compressed model, and now you can choose different trade-offs, and you get an entire RD curve for any possible choice of bitrate and reconstruction quality in a trained model. So how do you do that in high dimensions? Well, basically, you always work with a factorized variational distribution, and it turns out that this really allows you to do that on a coordinate by coordinate manner, which is very fast and efficient, right? So you can simply run this, the algorithm that we propose in high dimensional models also. Okay. How well does it work? So let's look at real valued examples. The first example that I want to discuss here is to actually compress a word embedding model, right? In particular, we looked at the probabilistic version of word2vec that we used in our previous ICML 2017 paper. So now you have word embeddings equipped with uncertainty estimates. And the metric that we want to analyze are hits at 10. In other words, how good is the compressed model once you reconstruct it at solving these word analogy tasks, right? So for example, if you look at king minus man plus woman, you're hoping that you kind of get close to queen. And in particular, you're hoping that queen is in your top 10 words according to the ranked list, right? So this is the y-axis that we look at. So what is then the x-axis? So this is essentially the amount of compression, or how aggressively we compress, right? So in other words, we're kind of really looking at a rate distortion trade-off. Again, when we compress more aggressively, we expect the model to not perform as well anymore in this kind of hits at 10 prediction task, but we want to have a good trade-off, right? We want to compress the model pretty aggressively while still getting decent results for still having useful word embeddings left. So as baselines, you can do something very naive. You just kind of take your most likely word embeddings, you quantize them to different decimal places, and then you use off-the-shelf lossless compression to kind of compress your discretized word embeddings. So this gives you the ensemble of baselines. But if you actually do, if you kind of use our method and you really compress the model in post-processing, taking into account that certain words are more certain than others, you get a much better rate distortion trade-off out. Right? And again, this is just to show you how versatile the method is. It's really very agnostic. It's not tailored to any particular data modality. You can kind of really use that in pretty much any Bayesian model that works with a mean field family. So you can also do that for image compression. And again, here the metric of interest is rate distortion performance. So those here are two slightly different metrics. One is more you know, the vertical axis are essentially image qualities measured in, you know, exponentiated L2 error essentially, and or a more visually appealing quality metric. People usually look at both. And then you see, you know, what kind of quality do I get out as I reduce the bit rate? And so what we see here is that if we take a simple variational autoencoder and compress it to different rates in post-processing, we get the solid orange curve out. And it's better than JPEG, and it's also better than all sorts of other quantization methods that you can do in post-processing, which are considered competitive. But we're not quite as good as the latest state-of-the-art neural network-based compression methods. And in some sense, it's to be expected because the baselines train separate models for every single point on the bit curve, right? So all of these, you know, black boxes here are separate models, whereas in our case, we have a single model that we compress in post-processing at different bit rates, right? So we're kind of not really getting at the gold standard, but we're still doing better than JPEG, right? And so this kind of just tells you that this is a pretty useful technique that preserves a lot of the underlying information that's already present in a variational autoencoder, but in such a way that you can really get smaller file sizes out if you use it. Okay. There are other certain interesting artifacts of this model, which makes it very different from any other compression scheme. The first one is that, you know, if you take a trained variational autoencoder and say on MNIST, which is shown on the top right here, and now you kind of compress it more and more aggressively, and you see what happens actually to the distortion, or how do the reconstructed images look like. You know, you get very different artifacts that you would get otherwise in compressions. Usually you would kind of get a lot of box-shaped artifacts, and ultimately the digit wouldn't be recognized anymore. In our case, the model tends to confuse images, right? So if you're kind of investing fewer and fewer bits, you're kind of you know, increasing your uncertainty region in latent space, and at some point the model just picks the mean of the latent space as the most likely encoding, and that oftentimes corresponds to a very generic letter. So in this or generic data point, in this case, it's 8, right? And if you do that for different data points, they all ultimately get converted or confused with one of the elements in latent space, right? The same actually happens also with faces, which is a pretty interesting, more like a curiosity here, a curious artifact of this model. Another potentially more useful artifact of the model is that actually the collapse prior costs close to 0 bits. Right? So a lot of deep generative models suffer from what's called posterior collapse, where certain you know, dimensions in latent space become useless because the variational distribution collapses to the prior and doesn't encode any useful information anymore. If you think about it, in our picture, when the variational distribution collapses to the prior, the dashed line here in this plot essentially gets flat. And so that means that you can use any binary bit string to represent your data. And so you would usually use 0.1, which is the cheapest and the shortest bit description of that. So in other words, you invest 0 non-trivial bits to encode a collapsed mode, which could be potentially very useful when you look at model compression. Okay. So let me move on and talk to you guys about another compression-related project, which is sort of similar in spirit, but yet also methodologically very different. But it really also draws on these analogies that I'm really interested in, namely in viewing compression as probabilistic inference and thinking about how can better variational inference, or how could potentially even MCMC or normalizing flows or whatever, better posterior approximation, how could they serve to actually achieve better compression performance in real world you know, image or video compression tasks. And before we get there, let me actually think a little bit more with you about why decompression or compression can actually be thought of as probabilistic inference. So it turns out if you think about classical compression, like image compression, oftentimes you have a unique decoding protocol that converts a binary bit string into an image, right? So this is pretty much the definition of the type of compression that you use, right? You cannot deviate from it. If you deviate from that protocol, you won't be able to reconstruct your data. So this kind of ensures interoperability between different implementations and so on. However, oftentimes there are different encoders. So for example, there's PNG Crush and there's Image Magic, and both of them can be used for encoding. And they're kind of both compatible with the same decoder, right? But they have different trade-offs. One is actually faster and gives you an image with a slightly poorer reconstruction, and the other one takes more time and gets you kind of the better quality out, right? So you can think of that as a way of doing inference on a given decoder, right? Where you think of these encoders as different kinds of ways of performing inference. So in other words, decompression is probabilistic inference. Given a unique decoder, you essentially want to infer an image's optimal latent representation. And again, there are different ways of doing that. And this opens up a whole new toolbox of variational inference methods that might potentially result in better compression quality. So this project, which hopefully will, well, don't want to say, yeah, so it's submitted to a top conference, and it looks good that it will be accepted. So this is now really looking at state-of-the-art image compression with deep learning models. And we're trying here to make it better, not by changing the model architecture, but only changing the inference procedure. And so the types of models that are currently giving you the best performance in image compression and really outperforming all sorts of classical codecs rely on two-level variational autoencoders, which are shown on the left-hand side here. So you have data X, then you have a first set of latent variables Y, which you use in order to discretize and entropy code your data. But then on top of that, there's a hierarchical prior. You have a P of Z, and then you have a P of Y given Z. And ultimately, what you want to do is you want to encode your image with the marginal prior P of Y, which is kind of integrating out over Z. In practice, you can do that, and you're kind of encoding two sets of latent variables. You're kind of encoding the image by memorizing a characteristic Z, and then also encoding P of Y given Z, and that allows you to compress the image. And inference or encoding in these models is as of now done pretty straightforwardly. You just have a variational autoencoder. You do amortized variational inference. So this is now plot B. You have inference networks F and FH, and they predict you the most likely latent state mu Y and mu Z based on the input. And then you round and entropy code pretty much in the similar way as we learned about before, but this time in a hierarchical model. Right? And during training, you basically train them as a variational autoencoder. So wherever you round, you're kind of injecting noise at a fixed variance. And again, as I said earlier, this basically guarantees that the latent representations are robust to rounding at that uncertainty. So what we want to do is something slightly more refined. Very simple idea, namely, can we improve the inference by essentially replacing the order 1 prediction of an inference network of mu and Z by more sort of an iterative procedure where we really refine the latent states of a given data point by running an internal optimization loop, getting better and better compression results. And so this idea was inspired by some earlier work that I did with Joe Marino and Yisong Yu, related works that go back to Krishnan and Matt Hoffman. So the idea is a very simple insight from people who are familiar with variational inference, namely that amortized variational inference is essentially just a way of speeding up variational inference. Before amortized VI became mainstream, people would do what's called variational EM, which is an optimization algorithm with two nested optimization loops. You have an outer loop and an inner loop where you refine the latent variables for a given set of generative model parameters. So let me explain that to you in case you're not very familiar with that. So the first bullet point essentially says that in amortized VI, we're trying to kind of, we have a variational objective function L, where we plug in our variational distribution Q that is constructed such that the optimized variational parameters lambda I for a given image xi are directly predicted using an inference network F that has parameters phi, and we're just tuning these parameters of the inference network phi. However, you can also say what we really want to do is we really want to optimize lambda I, right? So we actually don't care about F at all, and we're directly optimizing lambda I on an instance by instance level, right? So for every image, we're kind of optimizing that given image's latent parameters. And what we showed a couple of years ago is that that procedure can actually, again, be amortized. such that you actually don't have to run this nested loop, but you rather have an outer loop, and then you do kind of maybe some 3 inner optimization steps. And that already leads to a dramatic cost reduction and almost the same performance as if you would carry out the nested optimization. So we essentially want to explore this idea now in state-of-the-art image compression. And again, this is the model that we use. And it turns out it really works well. And I'm going to show you examples in the next couple of slides. Right? So this is just adopting this idea to the world of compression, where people have not really done this before. And it really leads a dramatic improvement of the image reconstruction quality. Yeah. So what we really did in this paper, improving inference for neural image compression, is we identified several potential angles at which image compression can be improved. And we postulated 3 suboptimality gaps in the conventional approach to image compression. The first one is the so-called amortization gap that I talked about before, that instead of optimizing the parameters of the inference network, maybe you should rather optimize the means and variances of individual images to kind of get better performance. So that can be thought of closing as closing the amortization gap. But there's also a discretization gap. So what you typically do is, when you train these compression models, is you instead of as a proxy of doing the rounding operation, you're actually injecting noise, because only that gives you a differentiable objective function. So in other words, what you do when you do inference is you're inserting these discretized latent states into the model, right? And so in other words, you're kind of maximizing over Q, over continuous states Q, and you're inserting the rounded version of Z into your objective. And that's always worse than directly optimizing over the discrete values, right? And so that's what we call a discretization gap, right? And that can be closed by directly modeling the encoded data as discrete, and it also works in a trained model, right? So this leads to a technique that we called Gumbel softmax annealing, and you'll see that it does pretty well. And the third suboptimality gap that we identified in this paper is what we call the marginalization gap, and that's actually pretty interesting, and it's a little harder to explain. But if you look at the hierarchical VAE architecture on the right-hand side, what you really want to do is you want to take your data point X and you want to encode it to Y, and then you want to compress Y with the marginal prior, right? So you want to really work with P of Y, which is the integral of P of Y given Z times P of Z dZ. But the problem is that you cannot compute it, right? It's still a deep latent variable model. So in practice, what people do therefore, as I said earlier, is they separately encode Z and then they encode Y conditioned on Z. Right? But this kind of leads to an overhead because you're kind of now dealing with 2 latent variables, and also you're making some approximation to that marginal P of Y that's optimal, right? So turns out there's something which is called bit spec coding, and that is probably too much to explain today, but it's a way of closing that marginalization gap. So bit spec coding is really a technique that allows you to compress data usually in a lossless fashion using the model's marginal density. And it was never really achieved to get that to work in lossy compression. And so this paper here for the first time shows how it actually also works in lossy compression. So that's kind of the third angle in this paper. So we looked at a whole bunch of different baselines here. Don't really want to go into detail, but we looked at state-of-the-art image compression that have been published in the last 2 years. We also looked at various very competitive image compression baselines like PPG, which is currently the best classical codec, and so on. And we also carried out various ablations. And this is the outcome of our study. It's a pretty interesting result. So what you see here is the rate savings relative to a baseline model at different values of PSNR, in other words, at different quality levels, right? So again, the x-axis is the quality level that you're interested in, and then the vertical axis show you how much bits do I save relative to some baseline. And in our case, the baseline is BPG, which is again the best classical image compression model, right? And now again, the interesting thing here is that we don't actually change the model architecture. The only thing we really changed is the inference procedure. So we always work with Minon's hyperprior model that I've already shown. And we see how much gains there are only by improving the inference. So first of all, Minon's model actually gives you the Brown curve. So this is kind of pretty on par with BPG, with better performance at higher quality levels. But then if you look at our proposed orange and blue versions, you kind of really get significant bit savings. As of now, this is pretty much state of the art. There's one paper that achieves something similar, but the fascinating thing here is that we really didn't change the model. And so our improved inference procedures can be basically combined with any new model architecture that comes on the market. And yeah, so let's look at qualitative results. Again, this is a typical image from the Kodak data set that people look at. You see the original image on the left-hand side with details of the face. And then BPG gives you the best classical performance. But maybe most interestingly, if you compare the fourth and the third images, with the fourth one being the base architecture by Minon that's doing amortized variational inference, with our model, which is proposed, that kind of shows you the benefits of doing iterative inference amortization and closing various suboptimality gaps, you see actually that in the same model architecture, you still get significant improvements out. Okay. All right, so I think we're kind of pretty much taking all the time. There's one last part that I wanted to cover originally, which is about scalable variational inference in MCMC, but I mean, this is actually a pretty old work by now. It's from 2017, and it's about, SGD is approximate inference, so maybe it's actually not so necessary to talk about that. So let me instead wrap up and come to the end of my talk. Yeah. So first of all, I really want to thank my group. So in particular, Robert Bamler and Ibo Yang, who did a lot of amazing work here. So they kind of both worked on these two recent compression papers. Robert is also the first author on dynamic word embeddings and will get a faculty position in Germany now. Rihan is another PhD student of mine who's now looking into video compression, really scaling it up to full resolution. And Joe Marino is also an amazing collaborator and currently a graduate student at Caltech. So to kind of summarize the talk here, I talked about variational inference as a way of providing a path to better compression. And the main papers we talked here about are posterior refinement by iterative amortized inference. So this is kind of this generic approach that we then applied to compression. I talked about the paper Variational Bayesian Quantization, which essentially is about compression and post-processing. You kind of take a trained VAE or some other model and you kind of compress it in some sense optimally. And then last, iterative and improving inference for neural image compression, our latest paper, which achieves state-of-the-art compression performance and shows that just improving the inference alone, you kind of get amazing performance gains on existing architectures, which opens up an extremely interesting avenue of research, in particular if you're interested in, like me, in approximate inference and looking into interesting applications of these refined inference algorithms. Yeah, so with that, I would like to close and stop here. And thanks everyone for your attention. And I'm here for any questions.
Thanks a lot, Stephan. If you have any question, please type it now in the Q&A box. In the meantime, I will use my privilege as a chair to ask my own questions. Sure. I was wondering in the first part of your talk when you mentioned this Kalman filter thing. So I guess in the Kalman filter, you have a model with latent variables and observed variables. I guess the observed variables are the vectors, the embeddings. The latent variable, what do they represent? What is their dimension? Do you use a much smaller dimension or?
Right. So actually, the latent variables are the embeddings themselves.
Sorry. Okay.
So yeah, it's actually kind of an interesting construction that goes back to Barkan in 2017. So he first proposed actually an interesting formulation of how you can understand word-to-vec as a probabilistic model, and it's actually kind of like before that, people thought it wasn't possible because you're kind of modeling every word conditioned on its context, and there's some sort of almost cyclic dependency. But the trick is essentially to not model the words directly, but rather to predict whether a certain word context pair is more likely to be coming from the actual corpus or more likely to be randomly paired, right? And so now you have like a binary model, and these probabilities are being obtained by taking scalar products of these word embedding models and looking at their, so that's kind of the modeling assumption. And
okay.
And then we simply tie the word embeddings and context embeddings directly in time using a Kalman filter, and everything can be trained jointly.
Sorry for the background noise. There's someone doing a vacuum cleaning in the corridor.
No worries.
All right. So actually, the latent variables, their dimension is pretty big, right? So it's going to be.
Yeah, I mean, usually they're kind of, I think, 100 or 300 dimensional word embeddings, and you have one separate latent variable for every word in the vocabulary, and actually have a twofold representation. Once as a word vector and once as a context vector. And yeah.
Okay, thank you. We have one question, but it's a comment actually from Abhinav Kumar, who says, "Thanks for a great talk. Can you share your slides for reference?" So maybe, yeah, sorry.
Yeah. Oh no, I can definitely do that. I mean, in fact, I have like on my website there is sort of a folder. If you know the path, I usually put my PDFs there. I guess I should just make that public. So then you can look them up there. I don't know if, Nikolai, right, if you want to publish slides also on yours.
May I take this opportunity to remind everyone that all our talks are uploaded on YouTube afterwards, so you can not only have the slides, but the complete talk. We have another question from Justine. For the iterative inference procedures, if I understand correctly, is the goal to make the variational posterior closer to the true posterior to increase the compression rate?
Yeah, so it's basically your, yeah, that's right. I mean, so you want to, or another way to look at it is you want to kind of get a higher elbow, because your elbow essentially really directly encodes your compression efficiency, right? The elbow has two terms, and one of them is reconstruction, and the other one is the rate. And if you get higher elbows, you kind of, or negative rate, and so yeah, higher elbows automatically translate into better compression, and doing iterative inference, you kind of get better elbow values. I mean, that's what you care about.
Okay. John is asked, can you recommend any, so we have another question from John. Can you recommend any technical MATIV resources for someone that is completely new to this kind of compression stuff? I was really not prepared for this talk.
Yeah, that's a good question. So I guess it's, I'm not sure if there's already kind of a great, review article or any overview material available. I mean, it's really that these kind of two communities, there's the classical image, or the, not only classical, but the image compression community that kind of sits in computer vision, that use deep learning, and they use deep learning to improve their performances. And then there's the generative model and Bayesian community, and only in the last 1 or 2 years, those communities actually merged. And yeah, I'm not sure if there's a great way to get an overview. You probably have to look into just the latest papers and just kind of go from citation to citation.
Can I throw in there, what do you think of David McKay's book, which is older than that, but tries to connect the two communities?
Oh yeah, that's certainly a great book in general, right? I mean, yeah, I mean, it's probably not revealing the latest architectures that are being used as of now, but I mean, they certainly, if you're interested in this kind of information theoretical, then this is certainly a great reference for sure. Yeah, there's also there are books on, information theory. There's also a book on minimal description length, by Risanen and Grünwald, I think. Yeah, so those kind of cover great background material, but they're not necessarily, giving you the latest exposure to the latest ideas.
So Pietro asked, can you please mention again the book that was suggested? So that's from David McKay.
Oh yeah, there's an old textbook. I'm not sure, is it I'm not sure when the latest edition came out. David Mackay might have been from the 90s still, late 90s. And I think it's actually publicly available. I think I think there's a PDF version, an official one from his website, if I remember correctly. I'm not completely sure. So I don't remember the title. It might be just machine learning, introduction, I don't know. And then there are information theoretical books, and one is Grunwald and others. And that's, I think the title is Minimal Description Length Principle or something like that, right? And that kind of nicely connects Bayesian machine learning with information theory and compression ideas.
Which is not something you see everywhere, actually. It's quite easy to have some background in machine learning or probability statistics without seeing anything from information theory, which is kind of a shame, I think. But, yeah. But David posted the link to the PDF, so that's great. I can't see any other question. So let's stop here and let's thank again Stephan. And we clap for everyone.
Thank you.
Sorry.
And again, I'm always looking for PhDs and postdocs, so please apply.
So may I take this opportunity to remind everyone we have another talk in less than a month by Chris Oates on the October 21st, if I'm not mistaken, but please double check on the website. And we have some exciting talks coming in November also as well, in December. So thanks again, everyone, especially thanks to Stephan for a very interesting talk. And goodbye, everyone.
Thank you.
Cheers.
Thank you.
Mm-hmm.